Hi, in this lectures, we are going to study the concept of normal and shear strains, which are the quantities used to describe the deformation of a body in engineering mechanics. To start, let us study an example in which we have an uniform bar like the one shown on the screen. Assuming this is the original shape of the bar when it is not subjected to any external forces or change in the temperatures. To understand how the bar deforms later on in different directions, let us draw some imaginary line segments within the body of the bar. Now, when an axial load is applied at the two ends of the bar, we will observe the following. First, when the loading is applied, the bar changes its shape and dimension. In engineering, such change is referred to as deformation. Second, the deformation not only depends on the location within the body, but also on the direction. For example, if we look at the imaginary line segments that we drew before, we can see that while the horizontal line segments elongates, the vertical line segment contracts. And finally, another observation is the angle between the line segments. They may also change. All of this indicate a need to define the deformation of a point within a body, which led to the development of concept of strains. Similar to the concept of stress that we learned before, strains also has two components, namely normal and shear strains. First, to understand the normal strain, let us assume we have a uniform bar fixed at one end like being shown on the screen. Then imagine we have a very short line segment oriented in the longitudinal axis of the bar like this. Like we saw before, the following is what will happen when we apply an axial load at the free end of the bar. Then the average normal strain of the bar is defined as a change in its length divided by its original length. And the normal strain for a point is defined as a change in length of the line segment delta S divided by its original length when delta S approaches to 0. As you can see, the normal strain denoted by the Greek letter epsilon is a dimensionless quantity. However, please note that sometimes it is also expressed as a ratio of length units such as millimeter per meter or meter per meter, etc. As we saw earlier, deformation not only causes line segments to elongate or contract, they also cause them to change the direction. So if we consider two line segments that are originally perpendicular to one another, then the change in the angle that occurs between them due to deformation is referred to as shear strain. This angle is denoted by the Greek letter gamma and is always measured in radian, which are also dimensionless. To illustrate, if we apply a force on the top surface of this block and consider the shear strain for the two blue lines. Then the shear strain, as defined by the formula on the screen, will be positive. However, if we change the direction of the force to the left, like the following, then the shear strain defined by the formula will be negative. So as you can see, whenever we talk about shear strain for a point, we need to define the two line segments. In the case of normal strain, we need to define the direction of the line segment. Now let us generalize the concept of normal and shear strain to define the deformation of a volume element for a 3D object as shown on the screen. Suppose what you are seeing at the moment is the undeformed shape of a point within the body of the objects. Now let's say because of external loads, the objects and the cube element deform like this. As you can see, our volume element changed its shape from a rectangular cuboid to a parallelepiped. We see that the deformed shape, the parallelepiped, can be defined from the undeformed one, the rectangular cuboid, using 3 normal and 3 shear strain. A collection of these normal and shear strains for an element or point is referred to as the general state of strain. Please note that while only small deformations are allowed in engineering design, they are exaggeratedly plotted in this presentation for visualization purpose. With all this visualization, I hope you have a clear understanding of the concepts of normal and shear strains. Thank you and see you in the next lectures.